Presentation in our properties unit entitled Changes. It says time may change me, but you can't trace time, the immortal words of David Bowie. So the goals for this particular presentation are that you distinguish between a chemical and a physical change, and that you weigh the evidence to determine if a chemical reaction has occurred. So here's what we already know. We already know that substances have chemical and physical properties that can be used to classify a substance. That's what we talked about in the previous two presentations. We know that chemical properties depend on the interaction with another substance, so it can't be measured independently, whereas physical properties can be measured independently. So that's the major distinction between a physical and a chemical property. Now, what we learned in the lab. We learned that some processes change the form of the substance, but not the identity. So for example, if you have a piece of paper and you tear that piece of paper in half, it's still paper. Okay, but what you did is you changed the form, you changed the shape, you changed the texture, those sorts of things. But some processes will change the form and the identity of the substance, and that's what you see whenever you see something burning. Now, just out of curiosity, you actually see them burning Harry Potter books. Okay, so that's interesting. Okay, so next, we have the physical change. A physical change is something that changes the form but not the identity of the substance. So if you take a cup of water and place it in the freezer, it's still water. It's just in a solid form. But the molecules haven't rearranged. You can just simply take it out of the freezer and it restores itself to water. Generally, physical changes are thought of as reversible, but that's not a good way of putting it because if you tear a piece of paper in half, it's really hard to restore the piece of paper back to the way it is. The best definition is you haven't changed the identity of whatever it is. You see this example right here. On a molecule, this is water. Water is referred to as H2O, where you have two H's and a single oxygen. So if you look, whenever you put water in the freezer, it's still H2O. It's just in a different form. Okay, it tends to be attracted to other molecules. We'll get to that in the next presentation. But it's still water, and that's a physical change. Now, physical changes come from whenever you change the shape. So if you take a substance and you fold it, you cut it, you rip it, you crumple it, those are all examples of changing the shape. And you can actually see, you take a dollar bill and you can fold it into the Millennium Falcon if you want to. Probably takes more than $1 to do that, but you get the idea. You've folded, cut, changed the shape, so now that it looks different, but it's still paper. You can change the temperature. Okay, if you take something and you heat it up, like you see a metal sword right here, if you heat up that metal sword, provided you don't get too hot where it reacts, okay, it's still just hot metal. If you take water and you put it in the refrigerator and it cools it down, you've changed the temperature, but you haven't changed what it is. What it does is it changes the velocity of the particles. So instead of that water molecule moving really fast, all over the place, it moves a lot slower whenever you put it in the refrigerator. But you've changed the velocity of the particles, you haven't changed what it actually is. Changing the state. Now, state refers to the phase of matter, and that's what we're going to cover in the next presentation. But solid, liquid, gas, those sorts of things. Did you change the phase, what it is? So ice, water, and steam are all H2O molecules. You can actually see all three are present here. You see the ice crystals, you see the liquid water, and then you can actually see here is steam, and they're all in the same tube. It's really hard to do. Next, you have changing the texture. Whenever you change the texture, it's still wood. You're not taking the machine and turning it from wood floor into a metal floor, but what you're doing is you're aligning the molecules a little bit more so they're smoother. And whenever they're smoother, that's what you say when you change the texture. So you've aligned the molecules to feel more smooth. Next, we have what's called a chemical change. And a chemical change is when the substance changes into something new. So if you have a cup of water and you put an electric current through it, it will actually split water into hydrogen and oxygen. Okay, so this is what we call a chemical change because you've changed what the substance is. It's no longer water. Instead, it's hydrogen and oxygen. So you can no longer say, hey, that's water. You can say, hey, that's hydrogen gas and that's oxygen gas. This represents what we call a chemical change. Chemical changes change from one substance to another, and it requires evidence that a substance has changed form. Or not changed form, changed identity. So you have to weigh the evidence in total because a single piece of evidence of a chemical change is not enough to say that a reaction has occurred. So for example, gas production. Two substances are mixed producing gas. That does indicate the formation of a new substance. If you take acid and baking soda and put them together, it produces bubbles. that is evidence that a chemical change has occurred. But just because there's gas produced does not mean a chemical change occurred. If you open a Coke and it produces gas, that is not a chemical change. The gas already existed in the Coke. There was already gas under pressure. There's gas bubbles already in the water, and all you did was let them out. So you have to be real careful when you weigh the evidence. You have to say, yes, there's gas, but why is there gas? Coke opening is not a chemical change, but mixing acid and a base is. If there's a sudden change in temperature, if you take two substances and you mix them together and all of a sudden it bursts into flames, that's evidence that a chemical change has occurred. Or if you take two substances and you mix them, all of a sudden it gets really, really, really cold, that's evidence that a chemical change has occurred because you have heat. Either production or heat being taken away indicates the formation or breaking of chemical bonds. We'll get into that in Unit 3. But placing metal in a fire is not an example of a chemical change, even though you have a sudden change in temperature. Okay, the sudden change in temperature, you have to look and say, is there an origin for this? Is there some heat source? Or is there something taking the heat away that is not involved in the chemical change? So you have to weigh the evidence. Next, precipitate formation. Okay, if you take two substances and you mix them together, usually they're aqueous and it produces a solid. So you take two liquids and all of a sudden a solid comes out. You say, wow, there's a solid there. There must have been a chemical reaction. Generally speaking, that's true. But if you take a solid and you add it to water and all of a sudden that solid's at the bottom, you can't say, wow, a chemical reaction occurred. No, all you did was pour solid to the bottom of the water. So you have to be real careful. If you're mixing two liquids and you get a solid, that's pretty good evidence. Okay, but if you're taking a solid and just pouring it into a liquid and saying, oh, look, there's solid, it doesn't work that way. If you have a color change, that can indicate the change in the substance because it's changing what is absorbed by the material. Okay, so it indicates the formation of a new substance. So if you take something, pour acid into it, and it turns pink, that's an indication that there's been a chemical change. However, if you take food coloring and put it in water, that is not a chemical reaction. All you did was have some colored molecules that somehow fit in there and make the water appear to be green. But you can actually kind of reverse that process. It takes a lot to do, but you can actually distill out the color from food colored water and you can get just the clear water back again. So just because it has a color change does not mean it's a chemical change. You have to once again weigh the evidence in total. If you have an odor change, okay, that's generally an indication that there's been a chemical reaction. It smells different. Okay, that's particularly true when we talk about combustion. Whenever you burn something, you tend to produce an odor. Okay, so it indicates the formation of new substances. But if you spray perfume, that does not mean there's been a chemical reaction between the liquid and the air. Okay, that's not a chemical reaction. Instead, that's just taking the substance that smells and spreading it out. So once again, you have to weigh the evidence in total. The next one is an apparent change in mass. Now, the reason why it says apparent is there is something called the law of conservation of mass. And the law of conservation of mass says that the mass does not change no matter what you do. But if there appears to be a change in mass, because maybe a gas was produced, or maybe it changed into a liquid and leaked out. Okay, those are indications that there could have been a new substance produced that your beaker couldn't hold anymore. So an apparent change in mass is an indication of a chemical change. You have to weigh the evidence in total. You have to investigate why there's a temperature change. Why is there a color change? And generally speaking, you're looking for two or more pieces of evidence. So if you have a color change and a temperature change, usually that's a pretty good indication that you've had a chemical reaction. You're looking for an odor change and a change in temperature, that's usually a good indication that there's been a chemical reaction. So an example, make a list of chemical and physical changes. What properties overlap on both sides? So if you were to look, the overlap is really what we're interested in because you have a physical change, could be color and temperature. That could be physical or it could be chemical depending on what it is. So you have to be able to weigh the evidence in total. It could be color, could be temperature, could be any of them depending on what they are. You really have to be able to say these things overlap and I have to say, okay, well, this is because of that. You have to weigh the evidence. In general, how many pieces of evidence are required? You generally need at least two, but the more the better. More the better. So if you have at least two, you can generally say, okay, well, this makes sense that it's probably a chemical reaction. 3, it says name one example of a physical change and a chemical change done in the kitchen when preparing a meal. Well, a physical change is really easy. If you change the shape of something by, say, chopping or cutting, okay, if you chop vegetables, okay, that's an example of a physical change. You've changed the shape. It's still a carrot, it's just a carrot that's been cut up. Chemical changes are a little bit trickier, especially in the kitchen, because whenever you heat things up, it tends to form a chemical change in the kitchen. So, for example, if you take all the ingredients for, let's say, eggs, okay, whenever you have eggs and then you heat them, the bonds actually break and they actually change the consistency of the eggs. Eggs is one of those weird things that actually becomes solid whenever you heat it. It's very different from most things. Most things, whenever you take ice and put it on a pan, it actually becomes liquid. But eggs are a little bit different, and that actually indicates that there's a chemical change. You have a change in odor. Okay, you don't really have a change in temperature, but you do have a change in color, change in odor. There's an apparent change in mass as the water tends to be cooked out of the egg. So you have an apparent change in mass. So there's a lot of evidence that a chemical change occurs. The last one says you mix ice, yellow Kool-Aid powder, and red Kool-Aid powder. You notice a distinct color and odor change, determine whether a physical or chemical change occurred, and justify your answer. So this is a really trick question. And the reason why is you see two pieces of evidence. You have a color change and an odor change. Okay, if you were to smell water, it has no smell. Well, at least if it's good water, it has no smell. Okay, then if you were to take Kool-Aid and smell just the Kool-Aid, Kool-Aid has a sugary type smell, so we're going to say it smells sweet. Now, when you mix the two together, it smells sweet. But it didn't change the smell of the Kool-Aid. All it did was add the smell of the Kool-Aid to the water. So you didn't have really an odor change for anything other than the water, and that's just because you put something that smells in it. Okay, once again, you have a color change. Okay, whenever you change the color, remember this is an example of you have something red and you have something yellow. Well, if you had a chemical reaction, would you want to drink Kool-Aid that had been reacted into something else? And the answer is no. What happens is the red and the yellow Kool-Aid mix together just like food coloring, and it becomes orange. But you could probably separate it out. Now you mix ice. Well, ice is going to result in a colder drink, but there's a reason. It's not like the bonds are reforming. You have something that is cold and you're mixing it together. So this is an example because it's a trick showing you that you can have all these pieces of evidence that you can explain away without saying that there's a chemical change.